Okay, so I hope that that first comparison test was pretty easy to understand. Let's look at the next kind of comparison test, which is called the limit comparison test. This one's not so straightforward. So let's write out the definition for it. Suppose we have sequence values that are always positive, again, two sequences, so b sub n and a sub n, that are both always positive. I guess it doesn't always have to be positive. It only has to be positive after a certain index. So eventually, they're always positive. If this is the case, there are three possible outcomes for the limit comparison test. The first one is the one that is used most often. If we have this limit as n goes to infinity of the ratio of a sub n divided by b sub n, if we can show that this limit is equal to some constant, where that constant is a positive number, then we automatically get that both, the series a sub n and the series b sub n both converge or both diverge. Okay, so just to kind of say what this means, if we have two sequences that we're trying to figure out whether the series converge or diverge, if we look at the limit of the ratio of the sequences, if that goes to a constant c, then that means that these two series are paired together. Either they're both going to converge or they're both going to diverge. So if we have a series that we're not sure if it converges or diverges, we're going to figure out another series that we know converges or diverges, and then use this limit comparison test. All right, 2 and 3 are very similar, just not quite as often used, but they're still important. So 2 here, again, we're going to look at the limit of the ratio as n goes to infinity of a sub n over b sub n. This time, if this comes out to be 0, and we know that the denominator as a series b sub n converges, then we automatically get that the numerator a sub n as a series converges. All right, so very similar if you look at the limit of the ratio, but this time if the ratio goes to 0 and b sub n as a series converges, then we also get that a sub n as a series converges. 3 is kind of similar, just the other way around. Same startup though. If we look at the limit as n goes to infinity of the sequence ratio a sub n over b sub n, this time if this blows up to infinity and we know that the denominator diverges, then we automatically get that the numerator also diverges as a series. Cool. Okay, so again, very similar kind of startup, but this time we have that the denominator there diverges. So let me find some good examples of this, and we'll do some examples. All right, so we're just going to do maybe a couple of examples that I found here in the book. I don't know why I didn't have these written out. I feel like there's a page of my notes missing, but that's okay. So the first one we're going to look at is this one. So this bottom one down here, we're trying to figure out if this series, 3/4 plus 5/9 plus 7/16 plus 9/25, which is written like this, 2n plus 1 over n squared plus 2n plus 1, if this converges or diverges. So just to write it out, it was 2n plus 1 over n squared. N squared plus 2n plus 1. I think that was it. Just double checking. Yes. Okay, cool. So the question is, does this converge or diverge? Okay, so again, you kind of want to go through the list. Start at the nth term test. Maybe try the integral test. And then from there, the only other option we have so far is the comparison tests. You could try to do a normal comparison test with one like this, but usually if I'm doing a comparison test, I try to jump to limit comparison test right away, just because there's a nice little process to that. The hard part is the same as the hard part from before. The hard part is choosing which series or sequence values to compare the original one to. You almost always want to compare this to one that behaves very similarly. So we want to try to find a sequence that behaves similar to the one that we have up top there, 2n plus 1 over n squared plus 2n plus 1. Almost always when you're looking at behavior, you're looking at the leading terms. So we can ignore the 1 on the back of this numerator, and we can ignore the 2n plus 1 in the denominator. Because when we do plug in big values for n, the n squared is going to take over. So if we're just looking at leading terms, what we end up getting is just 2n over n squared. That simplifies down to be 2 over n. What this tells me is that 2 over n behaves very similarly to 2n plus 1 over n squared plus 2n plus 1. So we're going to use the series 2 over n as our b sub n from the definition of the limit comparison test. So that's going to go in the denominator, and then the series I'm trying to figure out whether it converges or diverges goes in the numerator. The other thing that we would need to know is we need to know as a series, does 2 over n converge or diverge? I don't know why that happened. B sub n. So the series 2 over n, that's just the harmonic series that's multiplied by 2. If you remember back from, I think it was section 2, if we have a series that diverges, it doesn't matter what you multiply it by, it's still going to diverge. So that definitely diverges. So let's compare it. What we're going to do is we're going to take the limit as n goes to infinity of the ratio, and here's where it's going to get a little bit ugly for a minute, 2n plus 1 over n squared plus 2n plus 1, that all divided by 2 over n. So that's the ratio of a sub n divided by b sub n. All right, let's break this thing down. So what we're going to do here is we're going to just divide these two fractions. I'm going to leave the first one alone and multiply by the reciprocal of the bottom. So this n is going to flip up to the top and multiply on this numerator. This 2 is going to be multiplied into the denominator. So now it's still going to be the limit as n goes to infinity of, so in the numerator, 2n plus 1 times n is now 2n squared plus n. In the denominator, multiplying that by 2, it's 2n squared plus 4n plus 2. Okay, now we just need to figure out what this limit is. So this goes back to the section 1 stuff of finding limits of these sequences. For this one, we've looked at a bunch of these very similar to this. You have a couple of options. Technically, what you should do here is you should divide everything by n squared, and then you could see what it converges to. Another thing you could do would be L'Hopital's rule. So do the derivative of the top and the bottom. You might have to do L'Hopital's rule twice to get the answer. Or if you're pretty good with algebra, another thing you can do is just to look at the horizontal asymptotes of the function, either by graphing it or just by doing it algebraically. Because my numerator is a degree of 2 and my denominator is a degree of 2, they have the same degree, which means we're looking at the ratio of the coefficients on the n squareds, which is 2 over 2 or just 1. Okay, so what we just saw is that the limit of a sub n over b sub n goes to 1, which is a positive number bigger than 0. So if we go back to the limit comparison test, we are looking at part 1. We did the ratio and it came out to be a number bigger than 0. When it comes out to be a number bigger than 0, the series a sub n and b sub n are twins. They either both converge or they both diverge. Well, we already know what 2 over n does. 2 over n diverges. And because that one diverges and it came out to be a positive number for the limit of the ratio, thus, by the limit comparison test, we have that the original series up top there that we were first asked to find, the 2n plus 1 over the n squared plus 2n plus 1 diverges. And I'll write it all out. So this diverges since the limit of the sequence of the ratio a sub n over b sub n just went to a positive number 1, and we know that that series 2 over n, which was b sub n for us, diverges. Okay, let's do maybe one more example of this. I'll do it a little bit quicker. So just going back to the book here, let's look at what the next question is. That one's kind of ugly. I guess let's just do this one. So 1 over 2 to the n minus 1. So here we're looking at the series 1 over 2 to the n minus 1. Does this converge or diverge? All right, same startup, right? Try the other test. The nth term test would be inconclusive. We would not be able to do an integral test because you can't really integrate over that. So our next step is either the regular comparison test, which you could probably get away with, but here we're going to do the limit comparison test. For this one, we're going to use something that behaves very similar to that. That's going to be that geometric series 1 over 2 to the n. Again, remember that negative 1 isn't really going to do anything once my n gets bigger and bigger. This we know converges. It converges because it's a geometric series where the r value is less than 1. So now let's do the comparison. So we're going to look at the limit as n goes to infinity. I'm not going to type n go into infinity over and over again. Of the ratio. So it's going to be the a, which is the thing we're trying to figure out if it converges or not. So 1 over 2n minus 1 divided by the b sequence, which is just 1 over 2 to the n. All right, we need to simplify this down so we still have the limit. Again, we're going to flip it. So we're going to leave the first fraction alone, multiplied by the reciprocal of the second. We're going to end up having 2 to the n divided by 2 to the n minus 1. Oops, that's not how that's supposed to look. Let's put these in a big, maybe like this. Better. Okay, good. And then just, again, you can either do horizontal asymptote stuff. What you really should do for this one is you should divide everything by 2 to the n. So let's just write it out the way it should be written out. So that top is just going to be 1, right? Because 2 to the n divided by 2 to the n is 1. Down here, 2 to the n by 2 to the n again is 1, but then it's going to be minus 1 over 2 to the n. This term goes to 0, which means everything else is just going to go to 1. So again, we get the same thing that we got before. The limit of the ratio went to a positive number. Because this series converges, that means my original series also converges. Thus, by the limit comparison test, our series converges. Okay, cool. So that is section 4 in a nutshell. Moving on to section 5.